last day of CCS, and we start with the second keynote by Professor N. Asokan. Professor N. Asokan recently joined the University of Waterloo as a professor of computer science, and David R. Sheraton chair. He's also adjunct professor at Aalto University. Before joining academia, Asokan spent many years in industry research, first at IBM Research and then at Nokia Research Center. He's broadly interested in system security, and with particular emphasis on mobile platform security and the security and privacy of systems based on machine learning. Dr. Asokan is a fellow of ACM and IEEE. He's also a winner of ACM CCS Innovation Award last year. So without further ado, let's welcome Dr. Asokan.
Thank you, Shefang. So it's a pleasure and an honor to be here. And in particular, I want to thank the chairs because typically this keynote is on the second day, but they were kind enough to accommodate it for the third day because of my travel constraints. So I'm going to be talking about hardware-assisted trusted execution environments. And if I ask you how many of you know what a trusted execution environment is, I'm sure like a good number will put your hands up. But even more particularly, I'm pretty sure that each and every one of you has a hardware-assisted trusted execution environment in your pocket. Some of you probably have multiple of them. And this is not something new. If I had asked this question in CCS 2009, hardly any hands would go up as being familiar with trusted execution environment, but it would still be the case that the majority of the people in the audience would have a device with hardware-assisted trusted execution environment. But for a technology that's so widely deployed and for so long, it's not so well understood. In particular, the origins of why, how did this come to be developed, why is it so widely deployed, is not something that's widely known. So I'm hoping that I can use this opportunity to tell you something about the history of trusted execution environments, in particular mobile trusted execution environments. So just to set the stage, people understand different things by when they talk about trusted execution environments. So I want to sort of set the scope for what I mean by trusted execution environment for the purposes of this talk. So I mean any device that has hardware support for a few different properties. The most important one is isolated execution. By isolated execution, I mean that if you have a device that has like normal software, operating system and applications and so on, but has the ability to run some small pieces of trusted software that is strongly isolated from this other stuff that's running on the device, right? So if you have the ability to run something that in such a way that the other software will not be able to interfere with the operation of this trusted software, and also like learn what the trusted software is doing, we can call that isolated execution. And you can imagine why this is interesting, right? So suppose you have a smartphone and you want to do online banking, which is a sensitive operation, like a high-value operation. And if you want to authenticate to the bank, rather than doing it from an application that's running on the primary operating system, which has a large code base and therefore a big threat surface, if you can run some small piece of software that can authenticate you to the bank in such a way that that's isolated from this other piece of software, that would be a desirable feature, right? So maybe your bank would give you better access to your account or do high-value transactions if they can verify that you are coming from you're using a client software on your device that is protected from the large threat surface that this other software constitutes. So isolated execution environment is kind of the primary characteristic of a trusted execution environment. But you can do several interesting things if you just have isolated execution. But taking the example of, say, authenticating to your bank, you need to use some kind of credential for authenticating, right? And the credential itself should be isolated from the rest of the software, not just during execution, but in persistent storage as well. So that's the second property that I would characterize as being part of an isolated execution or trusted execution environment, is that the ability to store some data, such as cryptographic keys, in such a way that the trusted software can access that, but the untrusted, the other software wouldn't be able to access that even when the device is not running. And typically this is done by having a small amount of data, like enough space for, say, storing a cryptographic key, and possibly some read-write storage for keeping track of a counter. And if you have this within your trusted perimeter, you can turn any untrusted storage into protected storage with confidentiality and integrity guarantees. This is sometimes called sealing. So that's the kind of second property. And the third property is that suppose you have a device that has isolated execution and the ability to have protected storage. Now imagine that if your device could now convince a third party, such as your bank server, that you have such a device with such capabilities, then the bank server could, for example, give you better access than if you were coming from a normal Android or iOS application. This is called attestation. So if you can prove the property that you have an isolated execution environment and unprotected storage to either to another entity on the device, local attestation, or to a remote device outside. This is called remote attestation. So ideally, a trusted execution environment would have all three. And if you have, but the kind of fundamental requirement is that there should be at least isolated execution. The more you have, the larger class of applications you could support. And the reason why this is interesting is this is widely deployed now and has been for a long time. So just in terms of terminology, so this is what we would call a trusted execution environment, and typically this rest of the stuff is called rich execution environment. And the first sort of trusted execution environment that supported isolated execution dates back to more than 3 decades. IBM had these crypto cards, hardware security modules that were used in banks from the early 90s onwards. Trusted Computing Group, which is an organization that standardizes the so-called trusted platform module, started about 2 decades ago. But what led to really widespread deployment is trusted execution environments in commodity devices. The most important one is ARM. ARM has a technology called TrustZone, and pretty much any one of you who has a smartphone has ARM TrustZone in your smartphone. The chances are that you have ARM TrustZone in your smartphone. Intel, a few years ago, announced Software Guard Extensions, which is a trusted execution environment technology for x86 processors. And like I said, this has been deployed for a long time, and but hasn't been widely known and hasn't been widely used. So these are a couple of papers that we wrote 5 years ago when this technology has already been widely deployed but not widely known. But right from the beginning, even though it has been available for so long, right from the beginning there have been concerns about hardware-assisted trusted execution environments. And these concerns sort of fall into 2 categories. The first ones are flaws, either implementation flaws or design flaws that compromise the security guarantees that one would assume from this hardware basis of trust. So this is an example of a flaw in TPM from about 2007 or so. Just this week, there was another flaw in TPM where the secret keys could be extracted. This is an example of flaws found in TrustZone. And the most recent sort of spate of hardware vulnerabilities that I'm sure many of you have heard is against SGX. And perhaps the most well-known is Foreshadow. And this is not the only vulnerability, and this is not going to be the last. So even today, in this conference, there are a number of papers that discuss vulnerabilities in SGX. And this is, it's a safe bet that this is going to continue. So this is sort of one class of concerns, flaws in design or implementation. The other class of concern is the motivation behind this large-scale deployment. And this is also something that dates back to from the beginning of this technology. So here is an excerpt from the register, which I'm sure many of you know. It's a UK technology website reporting on Microsoft's introduction of a technology called Palladium in the early 2000s. And they were reporting on what Ross said about Palladium technology as being designed not to protect the interests of end users, but rather to sort of entrench the advantage of technology providers. A couple of months later, or a few months later, Electronic Frontier Foundation had a blog article where they said the inability for a remote party to ascertain what's running on your device, so in other words, the inability to do remote attestation, is a feature from a privacy perspective rather than a bug. So there have been this kind of concerns about this technology being designed and deployed, not for the benefit of the users, but for other considerations. But there have been also more sinister implications. So this is an article from a blog article from Joanna Rutkowska, who's a very well-known security expert, who wrote this when Intel introduced SGX technology, and she was questioning that if you're going to rely on Intel's SGX technology, you are essentially trusting Intel, especially if you want to do remote attestation, where the ability to ascertain what's running on your device has to start from trusting Intel certifying your device. And she's raising the question that in light of the events in the last 4 or 5 years, is it reasonable to trust Intel that there is no backdoor in this kind of technology? So given that there had been these kinds of concerns, it's sort of legitimate to ask, why is this technology so widely deployed? And furthermore, is it wise to rely on them? So what I'm going to do in this talk is to, like I said, tell you a little bit about my perspective of why this technology became widely deployed. And I'm going to do that in the context of mobile trusted execution environments, because like Xiaofeng said, I worked for Nokia, so I had sort of a ringside seat for why this technology was developed inside Nokia. So I want to tell you a little bit about this history that many of you might not know about. Then I'll talk something about the kinds of application that trusted execution environments have been used for. I hope to show you that some of these applications are actually good for users, even though that there are applications that constrains the freedom or flexibility of users as well. I'll briefly talk about the concerns or downsides of relying on hardware-assisted trusted execution environments, and speculate a little bit about what we can do about these downsides. And then, depending on if there's time, I can also briefly touch on other examples of hardware-assisted security. So let me start with this look back. Why is this technology so widely deployed, and not much is known about that, how it came to be? So mobile devices and mobile phones started taking off in sort of early to mid-90s, right? So in the beginning, they were essentially embedded devices that did two things: making calls and sending and receiving text messages. And mobile phones did these very reliably, even though these were sort of general-purpose computer systems that were in the hands of a large number of users. But they were closed in the sense that you couldn't extend the functionality of a mobile phone by installing software. But the people who were designing these, like mobile device manufacturers and operators, carriers, realized that allowing software developers to extend the functionality of these mobile devices could actually benefit the ecosystem as a whole. So there was this sort of drive to turn these closed platforms into open platforms, in the sense that software from ordinary developers could be installed on the phone platform to extend its functionality. There was this sort of desire to design and implement and deploy such an architecture. And PCs have been like this from day one, right? So right from the first IBM PC, any developer could write software, and as long as they could convince you as the user to install that software, they could extend the functionality of your personal computer. But mobile phones, because they started as this kind of closed systems, the move from closed to open system was sort of mediated by the different kinds of stakeholders who were already embedded in the ecosystem. So the first such stakeholders are operators, or as they would call in North America, carriers. So these are the entities like Vodafone and AT&T and so on. They build and maintain the infrastructure for mobile communication, but more importantly, they are the ones who have a relationship with subscribers, users, right? So you have a contract with them, they provide you services, they know how to bill you and get money from you. They had a number of business requirements, and they wanted to make sure that this transition from a closed system to an open system didn't affect their business requirements. So, for example, one business requirement they had was subsidy locks. So subsidy locks is when AT&T, for example, will give you an iPhone for no cost in return for you promising that you would stick with AT&T as your provider for the next 2 years, right? And carriers or operators wanted to make sure that mobile device manufacturers had the technical mechanisms to enforce this subsidy business model. And one way they wanted to do this is to ensure that every mobile device has an immutable identifier that can be then bound to the subscription, so that every time the mobile phone boots up, you could check to see this particular phone should be limited to a particular operator's SIM cards. Another example is copy protection. So those of you who are old enough might remember that operators or carriers got into the business of selling content in the form of ringtones. So in the early 2000s, you could buy a ringtone from your operator for $1, and it'll make your phone ring in a way different from every other standard phone. And operators wanted to make sure that this ringtone that you bought you wouldn't be able to sort of rip that and then give it to all your friends. So again, this meant that they need a way to authenticate the device, but more importantly, there should be some applications like the mobile phone application that should be able to access the ringtone, but some third-party application that you install on the same device shouldn't be able to take the ringtone. So there has to be a way to separate applications. So this is one sort of class of stakeholders. And if this stakeholder, mobile operators, were motivated by business requirements, the other stakeholder is regulators. And regulators are motivated by public interest, right? So protecting the interests of you and me. So for example, regulators have this process called type approval. So if a mobile device manufacturer wants to sell a mobile phone in a particular jurisdiction, they have to submit the design to the local regulator, and the local regulator has to approve sales. So in the United States, this will be the Federal Communications Commission, and every country or every jurisdiction has a regulator. So for example, one requirement of a regulator is that the radio frequency transmission parameters on a device should be stored in such a way that it cannot be manipulated either by the user or by some software on the device. So it turns out that the RF modem characteristics are different from phone to phone because of manufacturing imperfections. So typically when a phone is manufactured in the assembly line, it's turned on, calibrated, and then this calibration parameter should be stored on the device. And the requirement for type approval is that this stored data should not be changed easily without being detected. And the motivation for this is, again, public interest, right? So if you could transmit at a much higher power than everybody else, you're going to deny service for others. You might also cause a health hazard to yourself and to others around you. So regulators require that this storage of radio frequency parameters should be integrity protected. Another requirement is deterring theft. So it's big business to steal phones from one jurisdiction, especially the subsidy-locked phones, break the lock, take it across the border, and sell it at half the price. And again, regulators insisted right from the beginning that every mobile device should have a unique identifier so that they could build a theft deterrence mechanism based on these unique identifiers. And the last stakeholders are sort of ordinary users. So ordinary users are used to the simple devices that were reliable, that worked well, never crashed, and this phenomenon of, say, blue screen of death is unknown on mobile phones. And when the transition happened from closed to open systems, they expected that the same kind of reliability should be preserved. So this meant that mobile phones, as they transitioned to open systems, had a different starting point and therefore a different trajectory than what we are used to in personal computers. And some of that influenced the design and deployment of platform security mechanisms. So for example, in terms of software platform security, the most widely deployed software platform security architecture is J2ME, Java 2 Micro Edition. And at one time, I think about 2005 or so, more than a couple of billion phones in the world had J2ME. And even today, Android platform security architecture is the most widely deployed platform security architecture today, and even today it might not exceed the extent of deployment of J2ME. Shortly after that, there was a software security platform security architecture for Symbian OS, Symbian OS, for those of you who don't know, is a smartphone operating system. So iPhone is not the first smartphone, and iOS is not the first smartphone operating system. Symbian is designed and deployed by a local company, a UK company, and it was owned by the leading mobile phone manufacturers at that time, Nokia, Motorola, Samsung, and a bunch of others. And Symbian was derived from a personal digital assistant OS called Epoch. And Epoch OS didn't have a security architecture, but when they want to sort of extend Epoch and deploy it on smartphones, they realized that they need to be able to have a security architecture in the sense that even though these applications are all running on behalf of the same user, they should not have the same privileges. Each application should be afforded privileges depending on where it came from and what the user was willing to grant to that application. And when Android and iOS followed, sort of it became a routine that all of these, it's expected that all of these smartphone operating systems must have some kind of a platform security architecture. So that was for software, but the same thing happened for hardware platform security as well. So for example, I told you that there was this requirement that every mobile device should have a unique identifier, and there has to be a way of enforcing that. So one way to do that is to simply make it illegal to change your device identifier. And in fact, some jurisdictions have laws, including this country has a law that says if you change the identifier on your mobile phone, you are liable for prosecution. But of course, mobile operators were not satisfied with just having legal remedies, so they also required that there has to be sort of proactive mechanisms that would prevent or deter this ability to change your device identifier. And some of them made their way into standards. So this is an excerpt from a 3GPP standard. 3GPP is the body, third generation partnership project is the body that writes specifications for mobile communications, such as like 2G, 3G, 4G, and 5G mobile communications. And this spec from about 2001 says that the mobile device identifier, IMEI, the International Mobile Equipment Identifier, should not be changeable by software or physical means. And furthermore, they say that this is even a requirement for type approval that I told you about. So some of these requirements sort of made their way into specifications like this, where there's documentary evidence of these requirements sort of influencing mobile platform security architecture as they came to be today. Some others, like this storage of radio frequency parameters, there is no, at least I was not able to find any documentary evidence of this being a requirement, but this is folklore among people who are involved in mobile device manufacturing. So these considerations drove the design and implementation of this first trusted execution environments, hardware-assisted trusted execution environments, mobile devices. And the first one is a processor called Nokia Radio Application Processor, or Nokia RAP. So in the beginning, Nokia had mobile devices with two processors. One processor running the operating system and applications called the application processor, and another processor called the radio modem that runs the communication stack and authentication with the SIM card and so on. And the Nokia RAP was a trusted execution environment that was for the radio processor, the radio modem, and was used to enforce subsidy locks protection, for example. So shortly afterwards, so again, there is no documentary evidence of this, but shortly afterwards, Nokia was using processors made by Texas Instruments at that time. And Texas Instruments has a technology called M-Shield, which was announced and deployed about 15 years ago. And if you look at the M-Shield specification, it's sort of, it is possible that it was derived from this radio application processor architecture, but there's no way to verify this. Shortly afterwards, so M-Shield processors are based on a core designed by ARM, which is again originally a British company. And ARM then announced TrustZone with the same kind of functionality, like a trusted execution environment that supports isolated execution, secure storage, and so on. And it is, so if you look at this, the description of M-Shield, and if you look at the description of TrustZone as it is today, you can see similarities. But it is not known how much, what was the transfer, the technology transfer that happened between these different stages. So how much of Nokia RAP went into M-Shield and how much of M-Shield went into TrustZone is not very well known, because these technologies were developed as sort of in-house projects inside companies. So earlier this year, I asked a historian of technology to work with one of my students to try to document as much as she can about how this development came about. The problem with doing this project was that there aren't that many primary sources, documents that she can refer to, but furthermore, because this technology development happened inside companies, many of the people who are involved in that are still bound by non-disclosure agreements. So the only method that she had available to her was to do sort of an oral history project. So she identified like 15 different people who were involved in the technology development, interviewed them at length, and wrote an article summarizing what she found out about how this came to be deployed. So I'm going to take the next few minutes sort of giving you a flavor of what she found out. So I already told you that the process was driven by these different requirements like subsidy locks and tamper-resistant identifiers and secure storage. Another sort of very clear use case was mobile payment. So today, all of you I'm sure are familiar with things like Google Pay and Apple Pay, but already 2 decades ago, it was evident to mobile phone manufacturers and operators that if people have mobile phones and you could allow them to pay using mobile phones, that's going to be a big business. So this was also a driver for having hardware security support that would provide the necessary security for supporting this kind of application. So the first thought was, if you want a high level of security, then people already knew about smart cards at that point, so let's put a smart card slot on mobile phones. Right? And in fact, some companies even had products announced with this kind of functionality. So Motorola announced a phone with a credit card side smart card slot where you could insert your payment card and whatever. And this very clearly, very soon this became apparent that this wouldn't sort of scale, partly because mobile phones are commodity devices with thin margins, so having a smart card slot is going to put pressure on the sort of bill of materials cost. But more importantly, it's also kind of a usability problem, right? So even though smart cards technically can support multiple different credentials, typically every issuer wants to have their own smart card. So if you have a smart card slot, the user will have to swap between your bank, the card from one bank and card from another bank and a card from the government and so on. So this was the sort of problem that mobile phone designers were grappling with at that time. And Nokia designers came up with this notion of what one could call processor-secure environments. So this is, instead of having a smart card slot, do a set of minimal extensions to the processor so that you can support this other software and trusted software and separation between these two types of software in a logical manner, right? So you have the processor be in one mode where they run the operating system, but then switch to another mode which is isolated from the rest of the software where they can run applications for mobile payment and enforcing subsidy lock and so on. And what Sarah found out was that even though these use cases were known by higher management and they wanted to implement solutions, this particular technical approach of this processor-secure environment or the logical separation of running these two types of software in the same phone, this wasn't something that was sort of designed or required from above. This was sort of started out as a skunkwork project as a way to achieve all of these use cases with a minimal set of hardware extensions. So like any technology, this idea of logical separation between secure software and non-secure software, that goes back long before Nokia came up with this. So Sarah and Thomas, while doing this project, found patents dating as far back as like the early 80s, where you can sort of read, if you know how TrustZone works today, right? You have a secure world and a non-secure world, and the processor can switch between these two. You can read similar kind of wording in these patents, dating back to the 80s and 90s. But in the 80s and 90s, there were ideas and patents. What changed was in the early 2000s, when mobile device manufacturers were faced with problem, they designed a way And the first Nokia patent that we found was from 2002, which presumably was designed to sort of not infringe upon these previous patents as a way for widespread deployment. So shortly after Nokia had this patent, there's the first public documentation of this M-Shield technology from Texas Instruments. You can find this even today. And a couple of years later, ARM had this first published article about trust zone from about 2004. I don't have a link to this article because I couldn't find a sort of official place where this first trust zone article was published. But if you sort of Google for the title of this article, you can find all kinds of stash copies in multiple places. So by 2004, ARM has already designed trust zone technology, but there were more proprietary or limited trusted execution environments available and described long before that. And the first product I told you about was this Nokia radio application processors. Again, there's no documentary evidence, but the first deployment of a phone with M-Shield trusted execution environment technology was in 2004. And this also happens to be the first 3G phone that Nokia designed and deployed. So this was in 2004. And today, like I said, trust zone is widely deployed, not only for phones, but also for other classes of devices. So trust zone M is a technology that's intended for embedded devices like microcontroller units, which is much more efficient than the sort of traditional trust zone. So this is why this technology is widely deployed, because it was driven from these business constraints, and Nokia designers made this decision to have this logical mode, logical separation between trusted and untrusted software using processor support. And it's been deployed, first deployed in 2004, and by 2009, this was very widely deployed. So every Nokia phone had trust zone, but every smartphone at that time, whether or not they were using trust zone, still had trust zone support. But academia was sort of lacking behind in this. So when I first became involved, we wanted to sort of develop a system that allowed ordinary app developers to make use of trust zone technology that was widely deployed. And I think we did this work from about 2005 to 2008 or so, and we had a tough time getting it published, right? So I think we submitted it to this conference as well. Eventually, it was published in ACM CCS, and that was because academics didn't know what trusted execution environments were, and didn't sort of think that this was anything that deserves to be published in a top-tier conference. Fast forward to today, this has dramatically changed. So today, after this session, you're going to have 2 separate sessions on trusted execution environments, and there are papers on attacks against trusted execution environments, new applications using trusted execution environments, ideas for designing new features for the next generation of trusted execution environments. And so this is kind of a dramatic change in how the academic community views trusted execution environments. Part of the reason for this is Intel SGX. So trust zone, even though it was widely deployed, it wasn't easily accessible to developers, right? So academics couldn't play with that, because in the early stages, in the first few years, if you wanted to develop a trusted application for trust zone, you would have to pay thousands of dollars to buy the SDK from ARM, and even if you bought the SDK, it was difficult to develop software, and even more difficult to actually get it deployed. With Intel, that all changed. So if you wanted to play with SGX, you could download the SDK. You could buy an off-the-shelf computer with an x86, this sufficiently recent x86 processor, and then you can develop applications or try to find attacks and so on. So Intel essentially democratized this space, and in doing so, they, at least in the short term, they are paying the price for that, because close attention also means much more security vulnerabilities and flaws that were found, particularly against Intel. In the long run, I think this is good for science and good for Intel as well, but in the short run, the price of openness is to some level of bad publicity. So wide deployment was also followed by standardization. So the de facto standard for mobile devices, at least for the hardware and the firmware, is from ARM. But there are other standards bodies that define different kinds of APIs. So on Tuesday, you heard about trust routes. NIST has a recommendation for different kinds of trust route. trusted computing group that I told you about, which specifies TPM technology, has APIs that applications can use to access TPM functionality, and trusted execution environment functionality can be made visible via these APIs. There are also newer versions of TPM can be realized in software on top of hardware-assisted trusted execution environment. It started with the mobile version of TPM called MTM, but the current version of TPM 2.0, can be realized as a trusted application on a TE. But the dominant standardization body is called Global Platform. So Global Platform specifies a number of standards that allow a developer to write trusted applications independent of the particular trusted execution environment technology, so independent of trust zone or whatever other technology that you might come up with. They also have APIs that allow a developer, an app developer, an Android app or iOS app, to make use of this trusted execution environment functionality. And we'll come back to that a little later. So now that this technology is widely deployed, what is it being used for? So of course it's used, and it has been used for the kinds of use cases that drove the development of the technologies, such as tamper-resistant device identifiers, secure storage for radio frequency parameters, but any other data, mobile payments, boot integrity. How do you make sure that when your mobile phone boots, it's running software that is authorized in some sense? But once the technology was sort of deployed widely, both academics and other ordinary developers use this technology for all kinds of other applications. So I don't have the time or space to sort of give you an exhaustive list, but I want to give you a flavor of the different kinds of applications that were developed in my group, but also by others in the research community at large. So I want to sort of give you like a handful of examples. So the first one is something that we did a few years ago, when an antivirus company came to us and said they want to change the way virus scanning works on mobile devices. So 10 years ago, the way virus scanning worked was you install an antivirus client on your phone, on your PC, and then every day or every week, it will get an update of the sort of threat database. But all the checks were done locally, right? If you install an application, there'd be a local check to see if that application is potentially vulnerable with respect to the threat intelligence database that was on the device. So this was seen as wasteful because there was large amount of data being shipped out to these end devices. Most of them were never going to see any malware in the first place, and then particular malware that might eventually infect them. So there was a sort of drive towards keeping this threat intelligence database behind a cloud server and have sort of thin antivirus clients, which would, at the time of installing an application, would check to see if that particular application that you're installing is potentially hazardous. But antivirus companies realize that this brings a privacy problem, because now this means that your device has to tell this cloud server what applications you are installing on your device. And people have shown that if you tell what applications you have on your device to a person with machine learning expertise, they could essentially profile you. They could tell what your gender is, what your financial status is, what your political beliefs are, and so on. So antivirus companies wanted to be able to use this cloud-backed virus scanning technique while still being able to reassure their users that they don't have any more information than they did before. Right? So the natural way to do that is to use some kind of private set intersection technology, because you are installing an application that's characterized by some set of parameters, and the server has a database of such parameters, and you want to see if there's an intersection. But it turns out that for the characteristics of this particular setting, where one server has to deal with millions and millions of clients making simultaneous requests, private set intersection doesn't scale. So we ended up designing a system where the server has a trusted execution environment. The client device could use remote attestation to verify that server has such an environment, and then send the information about the application that's being installed to the server, so that the server can do the check and return, indicate whether it's a concern or not. And it turns out that this private membership test, where you have some key on your device, and you want to see if that key is part of a database that's in a server without revealing what the key is. This has many other applications. One application is private contact discovery. So when you install something like Signal or WhatsApp on your phone, it tells you which of your other friends are already on Signal or WhatsApp, right? So the way they do that is they ask for your address book, and then they send the address book to the server, and the server does a set intersection. And this, of course, is a privacy violation. So it turns out that, but if you could do private membership test, you could have this information about which of your other friends are using this application without revealing your address book to the service provider. So this is something that we published in like 2017, in the early 2017. A few months later, Signal, in particular the Open Whisper Systems implementation of Signal, essentially went down the same garden path. So they have a way of doing private contact discovery using a trusted execution environment on the server side. So this is just one example. There are a number of other examples that we did. Protecting password-based authentication, where the password is sent to the server for checking, but protected from the server itself by making use of a trusted execution environment. On Monday, my students presented SFAS, which is a way of doing outsourced computation where you don't trust the computation provider to do accounting. So today, if you want to outsource computation to Amazon or Azure, essentially you are at the mercy of Amazon or Azure to decide how much resources you are using. And you might be willing to do that for Amazon or Azure because they are big and they have a reputation to preserve. But 10 years from now, you might be outsourcing computation to a kid with a fast gaming computer in the basement, right? And there is this competing incentives where you are incentivized to underclaim your resource usage, and the computation provider is incentivized to overclaim the resource usage. And what we showed was how you can use a trusted execution environment on the computation provider side to balance this so that neither party could underclaim or overclaim. And so this is an example of what we did, but there are many, many other papers where trusted execution environments have been used for privacy-preserving machine learning predictions, privacy-preserving machine learning training, oblivious RAM, right? So accessing memory in such a way that the access patterns are not revealed, and so on. So some of these are, some of the original applications are indeed constraining the freedom of the users, but some of these other applications are beneficial to the users as well. So one interesting thing to note is that all of these academic papers that I told you about are on SGX, with the exception of the first one, which was on SGX and TrustZone. In contrast, practical deployments, commercial deployments, again, there are a number of them. Digital rights management is one. Runtime integrity, so Samsung, as part of their Knox platform, have a way of verifying the integrity of the kernel that's running on the sort of untrusted side by using a trusted application that's running inside TrustZone. Local user authentication, both biometric authentication but also password-based authentication, makes use of trusted execution environments on your device. Property attestation. So for a long time, Android had supported the possibility that when you create a key pair, you can specify that key pair should be protected by trusted execution environment on the device, so that the private key is not accessible in the clear to software, but accessible via an API and protected by the TEE. And now you can not only do so, but you can also convince a third party that your private key is protected by hardware on your device. So this is called key and ID attestation. So think about this example that I told you in the beginning. If you're authenticating to your bank, you can now convince your bank that you are using a signing key where the signing key is protected by hardware on your device. So all of these applications that are widely deployed are using TrustZone. And that might tell you something about sort of focus of academia versus focus in practice. Academia tends to do much of the work on SGX because it's easily accessible and easily experimented with, whereas the value in sort of real practice seems to be in making use of mobile trusted execution environments. So I'll come back to this question of downsides, which we started with, right? So I'm going to talk about two of the downsides. The first one is this difficulty of developer access, and the second one is risks of TE compromise. So I'm not going to talk about this, suspicions about the motivations behind why this technology was deployed, partly because your speculation is as good as mine. I cannot sort of throw more light on this, but these two things we can sort of discuss a little bit more objectively. So in terms of difficulty of developer access, there are sort of two difficulties. The first one is what I told you in the beginning, that when TrustZone, for the first, say, 10 years of TrustZone, it was simply impossible for an ordinary developer, an ordinary researcher, to play with TrustZone because the software development environment was not available, even if it's not available cheaply enough. Even if it was available, it was cumbersome to develop software. You make a mistake, the whole phone would crash, and then you have to wait for it to reboot. So this sort of playing with software was made more difficult. But more importantly, even if you manage to develop a trusted application for whatever use case you have, deploying that in large scale meant that you have to have the cooperation and permission of the device manufacturer or the carrier that you are working with. And there are perhaps two reasons why this was not made more open, right? So it wasn't possible for a developer to develop a trusted application and then deploy it on large number of devices. Initially, at least, there was no security architecture inside the trusted execution environment. If you could install a trusted application, it was as powerful as any other trusted application. So because of that, the development of trusted applications were constrained very strictly. So from my own experience in Nokia, there was one group in one city in all of Nokia that was allowed to write trusted applications because a trusted application is a dangerous thing, right? But the second reason is also that whenever there's a technology like that, business developers think that this could be a control point. They could make money off of that. So they want to sort of constrain who can develop and deploy software. So these are the kind of two difficulties in access for developers. In terms of the other problem of TE compromise, I think there are two classes of ways in which your TE could be compromised. The first one are sort of simply software attacks, right? So even though this TEs are hardware assisted, there is still a fair bit of software involved. There's a TE operating system, there's a TE application or trusted applications, which are typically written in low-level languages like C and C++, which have the accompanying problems with memory vulnerabilities that can be exploited and so on. And the second class of problems are what became popular in the last 3 or 4 years are side channel attacks, various kinds of side channel timing and memory access and microarchitectural side channels and so on. So I want to talk briefly about dealing with these downsides. In terms of ease of software development, the fact that Global Platform has these APIs changed the situation in the last 10 years or so. So now there are many development kits that are available from different sources. So for example, OptE has a SDK that allows you to develop trusted applications. It also has an emulator for TrustZone. OpenTE is something that my students did, which is a complete software implementation of the Global Platform APIs, so that you can develop your trusted application using your favorite development environment. You can use, I don't know, GDB for debugging and Emacs for editing and whatever, and you can get a trusted application that has the correct functionality. Open Enclave is a Microsoft-supported project that is intended to allow you to develop software for any kind of trusted execution environment. So eventually, I think their goal is to be able to write software that can run on SGX as well as TrustZone. So I think it's reasonable to say that it's no longer difficult to develop trusted applications. But the problem of having developed trusted applications, deploying that on a large number of devices without the permission of the device manufacturer or the operator, that's still a concern, right? So, and that sort of constrains the number of developers who can make use of trusted applications or trusted execution environment functionality. If you're a small developer or a university researcher, you can do this in small scale, but you cannot write a trusted application and deploy it in large scale. So the work that I told you about from 10 years ago, this was driven by frustration with this. So the trusted execution environment was deployed widely, but ordinary app developers were not allowed to use it. So we developed this system called onboard credentials, which was intended exactly for this, that any developer could come along and implement different kinds of functionality that needs hardware support, and then deploy that in such a way that they cannot affect the other applications that are also using the trusted execution environment, but also the platform itself. And then the way we did that is to essentially have protection domains that are created dynamically, right? So every trusted application is put in its own protection domain. And this was used for various things. So we worked with people from RSA who implemented Secure ID as a trusted application so that you can use your mobile phone as a token. There was also a ticketing application which was actually trialed in this Long Island Railroad extension in New York. Clearly, it was ahead of its time, 10 or 11 years ago. There was also an implementation of a SIM card. So what you know today as embedded SIM could be realized using a trusted execution environment, and one of my students had a SIM card implemented on top of onboard credentials. But the problem still is that even today, you cannot deploy this. So onboard credentials was deployed on Nokia devices and Windows phones, but it didn't sort of catch on. It remained proprietary. There have been wishes to do this kind of what one would call user-centric or consumer-centric provisioning rather than some kind of issuer-centric provisioning. So there are people from Royal Holloway here who wanted to have this kind of allow the freedom for a user to install whatever trusted application they wanted on their device without having to get permission from a device manufacturer and so on. Global Platform had a white paper that sort of articulated this wish, but it never became a standard. So this is still a problem. The second problem is hardware attacks, right? So I think it's clear after all these attacks that we have seen in the last several years that it's no longer reasonable to assume that hardware is inviolable. And then one could ask the question that if you can't rely on hardware, should we abandon hardware-assisted trusted execution environments altogether and rely on cryptographic techniques like multi-party computation? And there are reasonable people who argue for this. So my take is that these are not mutually exclusive, right? So TEs are still, so even though multi-party computation technology has made great progress in the last decade or so, even today, the performance and improvements you could get by using trusted execution environments is still an order to a couple of orders of magnitude better in terms of communication cost and computation cost. I saw a master's thesis from Thomas Schneider's group from this summer where they estimate something like 10 times faster computation and then 100 times smaller communication cost to realize the same kind of usage scenario, both using crypto with multi-party computation and using trusted execution environments. But they can also sort of serve as defense in depth, right? So if you're using multi-party computation, you have some credentials, you need to protect those credentials. You can either have a standalone device, which is running nothing else but your MPC client, or you can use a general-purpose smartphone where your credentials are protected using trusted execution environment locally. But the more interesting thing is it may be possible to detect and deal with hardware failure by exploiting application-specific cues or signals. And I want to take a few minutes to talk about that. So in general, you can either try to prevent failure or hardware failures, or you can try to be resilient against hardware failures. And there are sort of standard ways to do prevention, right? So one is formal methods. We have a good history as a community in using formal methods for protocols. There's also use of formal methods for this kind of platform security. SEL4, Security Enhanced L4, is an example of that, a formally proved microkernel that was developed from NICTAR, or what's called Beta61 in Australia. So this is clearly something that we should do as sort of good hygiene, although it comes with its caveats. So for example, SEL4 is a kernel that's proved correct, except that when meltdown happened, they had to go back and update their implementation because their assumptions didn't take into account the possibility of side channels like meltdown. The second thing that one could do is the level of sharing between this other software and trusted software. So this is a picture that I took from global platforms. If you want to implement trusted execution environments, you could do in different ways. You could have a completely separate external secure element, or you could have sort of a separate element within the same chip package, or you could have this process secure environment that I told you about, where the same process is in 2 logical modes. And as it happened, this is the dominant architecture now, which is what is followed by trust zone and so on. And the reason why this is the dominant architecture is this economic consideration that I told you about that Nokia engineers were faced with 15 years ago, right? So they wanted to have a cost-effective way of supporting these different use cases. Now you could sort of say that that design choice exposes allows sort of a greater room for hardware attacks because it's the same processor that's in 2 logical modes, it involves greater sharing. And if you have greater sharing, you have a greater level of exposure. And one way to deal with that is to introduce a separate secure element. And this is already happening. So Apple has their secure enclave processor, Google has a similar approach, and because these are physically separated, you could imagine making use of this for various purposes. So either using it for assuring the integrity of the device, or designing your application in such a way that the trusted execution environment functionality is shared between these 2 different TEs that are available on the same device. But I want to sort of tell about this last part because I think this is promising. So if there is a way to exploit a hardware fault, that might leave telltale cues from an application-specific sense. And if you can detect that using application-specific knowledge, that might be one way to recover from that. So I want to give you this example of the system called proof of elapsed time, which is a technology that Intel proposed as part of their Hyperledger consortium contribution. So POET is a replacement for proof of work. So you all know how proof of work works, right? It's a way of deciding who gets to choose the next block in a blockchain. And the way it's decided is by having everyone solve a cryptographic puzzle, and whoever solves the puzzle first is the winner. And the difficulty of the puzzle is distributed according to a certain distribution. What Intel does is essentially achieve the same distribution, but instead of making each processor do a lot of work which consumes electricity and so on, simply force the device to wait for a certain time, chosen from that same distribution. And then at the end of that waiting period, the trusted execution environment will give you a certificate saying that you have waited that long. So this means that whoever gets the certificate first will win the right to make the next block. So of course, if your trusted execution environment is compromised, then that party is going to win this election in every round, right? So if you look at the normal distribution, a party might legitimately win many times in a given unit of time, but typically you would the majority of them would win some number of times, and the unlucky ones would be sort of further to the left. POET's observation is that you can pick a boundary here and say no one is allowed to win more frequently than that bound, and it may be because they got lucky, or it may be because they compromised their trusted execution environment. But if you could do this, then you essentially change the impact of hardware compromise from winning every election to winning in proportion to how many devices you control. And essentially, this is using application-specific knowledge to mitigate the effects of hardware compromise. And so I stole the next 2 slides from Frank Peasons, who basically had this notion of cross-layer design for security, and he drew his inspiration from the Turing Award talk from Hennessy and Patterson, who said that if you have a vertically integrated application rather than sort of nicely layered application, the performance improvement can be like orders of magnitude better. And Frank's observation is that the same thing applies for security as well, not least because the adversary is going to use cross-layer information to make the attack more effective, and therefore defenders should also be able to use cross-layer information. So using application-specific information rather than observe strict sort of separation. And he gave an example of some of their past work where they did software fault isolation by making use of the knowledge that application has, but which was thrown away during compilation. So at runtime, that knowledge was not available. By sort of retaining that information, you could protect against software fault isolation. And this is, I think, a promising approach. So I'm not going to talk about this other hardware support because I'm out of time. If you have strong feelings about hardware-assisted security, I was asked to do a special issue for IEEE Security and Privacy magazine dealing with sort of not only attacks against hardware support, but also new ways of doing hardware support, new ways of designing trusted execution environment, and so on. So if you are interested, I would encourage you to submit an article. So I want to leave you with this. I'm not going to read through that. But essentially, trusted execution environments are widely deployed. The current dominant architecture was driven by economic considerations. It's no longer possible to rely on hardware security as an absolute, but there may be ways of detecting hardware compromise by using this kind of application-specific or cross-layer information. And because of that, I think one shouldn't just throw away hardware support for trusted execution environments, but try to use it as one layer of defense. So I would stop with that, and hopefully we have some time for questions.
We do have 15 minutes for questions.
Adrian Perrick from ETH. So I looked at the observation about that these systems oftentimes get broken, and that's a really interesting aspect. And so that was one of the reasons for software-based attestation or timing-based attestation, where you do not rely on any secrets of systems. And so just yesterday, I saw this TPM fail attack that just came out, where private keys can be extracted from some TPMs. So with this, it seems there is a space for software-based attestation to be able to, when you have physical possession of a device, you can actually execute secure operations and ensure that the correct code is executed on a device. So how do you see these technologies in assistance to the hardware-based mechanisms?
So I agree that I think software-based attestation removes one assumption, and therefore it is, has its role, except that it also comes with constraints, right? So you cannot do this kind of remote attestations with a bank that's far away if you are relying on strict timing constraints. So it has a role, certainly with sort of attesting peripherals, for example, but it wouldn't be a drop-in replacement for all the settings where you would use hardware-based attestation.
Right, certainly not. But in order to recover from compromises, like or from attacks, when you want to rekey the device, you could actually use these techniques to create a root of trust and then build on that to do the update or to rekey the device. Right.
So I think, so already now there are like many efforts and sort of thinking about the next generation of trusted execution environment. There's like open source hardware project and so on. And I think now is the time for this kind of thing to sort of do our sort of second edition of how to design trusted execution environments.
Eric Wistro, University of Colorado. Thanks a lot for the talk, really interesting history. I guess mine's a follow-up question sort of on that about where you see the open hardware and things like RISC-V or even FPGA-based solutions. It seems like that's sort of the last step to making all this open, from the open source hardware or software doing SDKs and more wider availability. This is the last step. Where do you see that now? Where do you see that going in the future?
So I think this is especially the part that I didn't address, like this risk of backdoors imposed by governments and so on. I think the answer to that is going to in this direction of open source hardware. And from what I understand from talking to companies is that companies are now interested in RISC-V based solutions precisely for this reason, that not only do they want to have secure technology, but they also want it to be seen as trustworthy. So I think both for academics but also for actual deployment, open source hardware is going to be prominent going forward.
Thanks.
Hi. Securing systems is not something that you design and you forget and it's there. Especially with modern architectures, it's an ongoing process, an ongoing process, an ongoing process. And if it's software-based, you can do updates through the cloud. But if it relies on hardware and something breaks, it's a more catastrophic break. And if it breaks and we don't know about it, it's still good for marketing but not good for security. So there are certain weaknesses beyond the ones that you mentioned, I think. Can you elaborate?
Yes. So I think one way to address that is having these mitigation techniques that don't rely on even detecting that something is broken, but like what I told you about this POET, right? So you don't even know if hardware has been compromised, but you design the system for that particular usage scenario in such a way that even if hardware is compromised, the application level guarantees for the whole system is preserved. You're right that you cannot touch hardware the way you do unless you deploy FPGA-based solutions, and again, you have to rely on some hardware as the basis, and then the vulnerabilities there cannot be patched. I think it's a kind of a balance between where you draw the line and for your co-design.
Thanks.
Hi, Charles Weir, Lancaster. From the point of view of a software or app developer, the TEs feel a bit like the crypto APIs that a lot of people have been talking about. It's fascinating stuff, and I want to rely on it, but actually for anything I might realistically want to do, a TE is far too low and gritty. Yes. And I know if I use what's in my LastPass, it has some sort of fingerprint on it, and I bet you anything LastPass haven't programmed the TE, but they are using it in some way. Yes. So I wondered if there's also a movement to provide sort of application level primitives that use the TEs but aren't actually sort of involving programming or anything.
Indeed, good point. And I think this is happening. So Android Crypto API has been doing this for a long time, that when you, for example, when you create a key pair, you could indicate that you want it to be protected by hardware-backed key store, and the way you would create a key and use it is exactly the same as what you were doing before, except for this indication. So you're right that the vast majority of developers are not going to be writing trusted applications. They are going to be using APIs, and then the question is sort of what APIs are needed. And so right now the technology is at crypto APIs. Crypto APIs support this with more and more functionality, like, for example, now you could do key and ID attestation, which you wouldn't normally do with software crypto API, but if it's hardware-backed, then it would make sense to attest that. So this, I think we are still sort of discovering where this line would be, but it's true that writing the full Turing machine capability of a trusted execution environment is not necessary for vast majority of developers.
Thank you.
Hi, Fan Zhang from Cornell. So one thing I guess with trusted hardware is when the hardware is deployed, you actually are not only trusting the hardware itself. For example, with SGX, you also need to trust Intel to run the attestation service correctly. And also, Intel is responsible for managing the attestation keys and the other secret keys that are embedded in the hardware. And this process is largely opaque at this point. And do you see a movement that, and also the reasons behind that may be complex, right? Intel may have a commercial interest in maintaining this closed. So do you see a movement to a more open and standard process like this?
So I don't think there's any technical reason why this attestation process needs to be as complicated as it is now. Intel, of course, knows their own reasons. One of the reasons I suspect is it's also having control over compromises, right? So if they would have a open attestation mechanism, they wouldn't be able to quickly react to compromise. By having all attestation go through them, they could potentially react quicker. Having said that, there is nothing that says Intel has to do the attestation for SGX, right? So assuming that there is some kind of open source trusted execution environment implementation, there could be a third-party body that could, you'll have to sort of design the logistics, how do you sort of bring a device into this attestation system, but in principle, anybody could run the attestation. I don't know of any development like that, because it, again, not only requires the design, but also requires the sort of incentive to be able to run the system. But with open source hardware, it is possible that we'll end up with something like that. But I don't know of an initiative like that right now.
Okay. Thanks.
Asokan, Sanjay Shah from the University of New South Wales in Sydney.
There has been a lot of talk about security in IoT, and there was a keynote on PUF. We did TPM chip on IoT about 10 years back, not IoT, but on embedded sensor devices. What's the future direction in your mind?
So, like I said, there is a variant of trust zone for MCU class devices, which is very fast in switching between this kind of normal world and secure world. This is already commercially available, and people have been not only using it, but also attacks against this have been kind of recently announced. I just saw that the next CCC Chaos Computer Congress is going to feature an attack against Trust Zone M. So I think this is happening already, that sort of trusted execution environments for very low-end devices with low overhead is right now it's only ARM, but I'm sure there will be other types of trusted execution environments as well.
Thank you.
Other questions? Okay, I do have questions about the diversity of the T. Mm-hmm. And right now we have SGX, we have trust zone, right? Mm-hmm. And for the T developer, for example, Intel, when they first built up SGX, it was designed for DRM. Then later it evolved into it's a username T. It has a huge attack surface. Mm-hmm. But later it evolved into something which they even think about including operating system inside Include, which was not, personally I don't think SGX is designed for this purpose, right? And one possibility in the future is we have a different application domain. For different application, we have a different T. And because you don't need to design a T which can serve all the purpose. So the question is, how do you think about the future, not only individual T design, but the whole ecosystem about interoperation across multiple T and how they work together, and the diversity of T in the future? Do you have an idea about it? Mm-hmm.
So first of all, I don't think, well, again, I can't speak for Intel, but I don't think Intel designed SGX for DRM the same way as what I explained about mobile TEs, right? They were not designed for DRM. DRM was one application, but there were other applications that were sort of not focused on constraining the user, but rather protecting the user. I think this is an economic consideration, right? So the reason why we have sort of one general purpose TE platform that can serve multiple applications is because the cost of designing a separate type of TE for each type of application was seen as prohibitive for commodity devices, right? So maybe from some specialized environment like military application, there could be a custom-built TE, but I think as long as we are talking about sort of consumer devices, I don't see this happening, that you would have different types of TEs for different applications for the reason that it's going to drive up the cost pressure. But you're right that the result of that is lack of diversity, right? So you have only one TE architecture for mobile devices and another one for x86 processors right now.
And I think this is, just for IoT, definitely you need some low-end T protection, right? And SGX designed more like for the desktop low-end server. But right. For high-end server, for example, you have accelerator, you have a GPU. Right. They also need T protection. Right. There's no such technique.
Right. That's a good. So this is actually an active area of research now that you can have SGX on a processor, but you offload part of the processing to a GPU or a neural computing unit, and that breaks your guarantees because now the data that you want to protect is available outside for reasons of performance. So there have been recent papers in the last couple of years trying to do this end-to-end security for external peripherals like GPU and NPU. But there is no solution that you can sort of readily available. It's still an active research topic.
Okay, thanks, speaker again.
Thank you.